Okay, so this time we're going to find infinite limits at infinity, and we're going to look at asymptotes. Now, before we actually do some problems, we need to look at some graphs. For example, let's look at this graph, and let's find the limit as x approaches 0, because at 0, the function is undefined. So let's see what happens. So if I take the limit as x approaches 0 from the left of 1 over x squared, let's follow along. So as I move along the x-axis towards 0, you got to look at your graph. What's the graph doing? The graph is getting larger and larger, and it grows very, very large, and it becomes unbounded. So we say that it goes to positive infinity because it's going in the positive direction. Now, as we approach, well, let me write it out first. So if I have a limit as x approaches 0 from the right of 1 over x squared, and if we do the same thing where we're approaching 0 from the right, what is happening to my graph? My graph is getting larger and larger. It's increasing without bound, and it does not reach a certain y value. It just keeps on getting larger and larger. It goes unbounded, so therefore it goes to positive infinity. So the one-sided limits, they both go to positive infinity, but if I want to know what is the limit as x approaches 0 of 1 over x squared, you can't say that it approaches positive infinity. You have to say that the limit does not exist. The one-sided limits, yes, you can put positive infinity, but the actual limit as it approaches 0, meaning from the left and the right, we say it does not exist. For this next example, I want to do 4 limits. I know the other one only did 2, but let's do 4 on this one. So one is we want to approach 0 because if we look at the denominator, when x is 0, the function is undefined. So let's see what happens when we take the limit. So first one will be limit as x approaches 0 from the left of 1 over x. And let's just follow the graph. As x approaches 0 from the left, my graph is decreasing without bound. Again, as x approaches 0 from the left, my graph is going in the negative direction. It is decreasing without bound. So we say that it's going towards negative infinity. Now, if we check the other side, limit as x approaches 0 from the right of 1 over x, and we do that again. As we approach 0 from the right, what is the graph doing? You got to follow the graph. So the graph is going towards positive infinity. It's increasing without bound. So as x approaches 0 from the right, the graph is increasing towards positive infinity. So you say positive infinity. So since the one-sided limits are both going in opposite directions, and they're both one of them is increasing without bound and the other one is decreasing without bound, we say that the limit as x approaches 0 of 1 over x does not exist. Okay, now the other limit that I wanted to look at is what is the limit as x approaches infinity of 1 over x. So x is approaching infinity. It just means that what happens as x goes towards infinity this way, to the right. So if we follow the graph, you'll notice that it's getting closer and closer to the x-axis, and the value at the x-axis is 0. So therefore, the limit is getting closer and closer to 0. So this will be 0. And then the last one, which I'll do on this side. So limit as x approaches negative infinity of 1 over x. So if you follow it, negative infinity is in this direction. So what's happening as x goes in the negative direction? Your graph is approaching the x-axis again, so it's getting closer and closer to 0. Now what I want you to notice now is this. If you go back and notice that in this one and this one, as the denominator got smaller and smaller, meaning it got closer and closer to 0, the limit went to one of the infinities. So as your denominator gets smaller and smaller, the actual answer gets larger and larger and larger. If you don't believe me, take out a calculator and start dividing numbers that are close to 0, and you'll see that it's right. Also, what I want you to notice is this, that as x gets larger and larger in the denominator, because that's what really means as x goes to infinity, it's getting larger and larger, the actual answer is approaching 0. Okay? It doesn't matter in which direction, whether it's positive infinity or negative infinity. If the denominator is heading towards one of the infinities, the actual answer is always going to be 0. And once again, if you don't believe me, go ahead, take out a calculator, start dividing 1 by large numbers, and you'll see that it will approach 0. Okay, so when you take one-sided limits, there are 4 possible one-sided infinite limits of a function f at c, meaning this. For example, if we approach c from the right, one possibility is that my graph is increasing without bound, and therefore it goes towards infinity. So the limit as x approaches c from the left of f of x is infinity, meaning it doesn't have a y value or an actual value, because infinity is not a number. It just says that it keeps on growing forever. Another possibility would be that as you approach 0 from the left, what is your graph doing? In this situation, the graph is decreasing without bound. Since it's decreasing, that means that the limit is going towards negative infinity. The other possibility is that if you approach c from the right, what's the graph doing? Follow the graph. The graph is increasing without bound. So it's increasing without bound in the positive direction. So that means that the limit is infinity. And the last possibility is if you approach c from the right, again, c from the right, what's the graph doing? The graph is decreasing without bound. So therefore, that means that it's going towards negative infinity. That will be the limit. Now, if we know the graph of a function, we can use it to investigate infinite limits. So let's see. So infinite limits. Let's look at this first graph. So this first graph is a graph that we should all know. It is y equals natural log of x. Now, if you approach, before I do that, the domain of natural log of x is x has to be greater than 0, has to be positive. So therefore, if we approach 0 from the right only, not from the left because it's undefined on that side, but from the right, what's the graph doing? The graph is going towards negative infinity. It is decreasing without bound. So for this one, we can write that the limit as x approaches 0 from the right of natural log of x is equal to negative infinity. Memorize it. It'll come up again. Okay, so now we have tangent. So if I want to find the limit as x approaches c, in this situation c is pi over 2. So if I say limit as x approaches pi over 2 from the left of tangent of x, let's see what happens. As we approach pi over 2 from the left, the graph is increasing without bound. So therefore it is going towards positive infinity. For positive infinity, you don't have to write the positive in front, just leave it out. Now if we investigate the other limit, so limit as x approaches pi over 2 from the right of tangent of x equals, and if you follow your graph, first let's approach pi over 2 from the right. There it is. What's the graph doing? The graph is going towards negative infinity, so therefore the limit is negative infinity, and therefore the limit does not exist. Okay, let's look at secant again at pi over 2. So if I look at limit as x approaches pi over 2 from the left of secant of x, so we're approaching pi over 2 from the left. Pi over 2 from the left, the graph is going towards positive infinity. It increases without bounds, so positive infinity. And then the last one, or the other one, the limit as x approaches pi over 2 from the right of secant of x. Let's see, as we approach pi over 2 from the right, the graph is going towards negative infinity. So as we approach pi over 2 from the right, the graph is going towards negative infinity. So this limit would be negative infinity. Let's do one more graph, actually two more graphs. So this time we have the graph of cosecant, and the c is 0. So we're going to say limit as x approaches 0 from the left of cosecant of x. So again, let's follow it again. So we're approaching 0 from the left. What's my graph doing? So we're approaching 0 from the left. The graph is going towards negative infinity. It is decreasing without bound, so negative infinity. And if you look at from the right side, the limit as x approaches 0 from the right of cosecant of x. So as we approach 0 from the right, my graph is heading towards positive infinity. So we're approaching 0 from the right. The graph is going towards positive infinity. So the limit as x approaches 0 from the right of cosecant, it is just infinity. And the last graph, let's see, cotangent. Again, the c value is at 0, so we're going to start with that. So limit as x approaches 0 from the left of cotangent of x. Again, let's look at the graph. We're approaching 0 from the left. What's the graph doing? We're approaching 0 from the left. The graph is heading towards negative infinity. And if we do the other side, so limit as x approaches 0 from the right of cotangent of x. So as I approach 0 from the right, what is the graph doing? The graph is heading towards positive infinity. So as we approach 0 from the right, the graph is going towards positive infinity. So the limit does not exist. So limits of quotients in which the numerator is a non-zero number. So the numerator is a non-zero number, meaning it's not 0. It's whatever number except 0. And the limit of the denominator is 0, often results in infinite limits, meaning that if you want to take the limit and the denominator is approaching 0 and the numerator is not, then you always get infinite limits. And these are examples of that, because here the denominator is approaching 0. The numerator is just a number that is not 0. And look at the limits. They both go to infinities. They're infinite limits. Same thing here. The denominator is approaching 0. So therefore, the limit becomes an infinite limit. Okay, so now we're going to find some limits algebraically. And usually what I've told you before is go ahead, just plug in. Let's see what we get. So if we just use direct substitution and you plug it in. So here we have the limit as x approaches -4 from the right of this rational function. So let's just go ahead and plug it in. So -4, so 2 times -4 plus 1 over -4 plus 4. We're going to end up with, in the numerator, we get -8 plus 1 is -7 over 0. That's a problem, so we cannot have that. Now, since we got 0 in the denominator, we need to know, since we're doing it from the right, remember what I said earlier? I said that if the denominator approaches 0, then the limit approaches an infinite limit, which we need to know, is it positive or negative. So the way to find out is to do this. So I'm going to erase the 0, and what I'll do is I'm going to make a little number line here just so you can visualize this. And I'm going to say -4 here. So if we are approaching -4 from the right, now remember what other numbers we have over here. We have like -3, -2. But what I want you to focus on is that as we get closer and closer to -4 from the right, what does the denominator become? It's getting closer and closer to 0, yes. But is it a positive number or a negative number? Well, since we are approaching from the right, that number is going to be positive. So this is how we'll write it. We'll write it like a little plus sign here. And that just tells me that that number is getting very, very small. It's approaching 0, but it's positive. So now, when I take the limit, I notice that my numerator is negative and the denominator is positive. And when we divide a negative divided by a positive, we get negative. And since the denominator is approaching 0, that means that the actual limit, the answer, is approaching one of the infinities. In this situation, it'll go towards -infinity, so that is the limit. Okay, so this one, we want to find the limit as x approaches 0 from the left of this rational function. So again, let's just do direct substitution. I'll do it down here now. Let's see, so it'll be numerator. If I plug in this 0 into there, 5 times 0 is 0, plus 3 is 3. So we get 3 in the numerator. If I plug in a 0 there and there, we're going to get 0 times -1. And 0 times -1 is just going to be 0. So we don't want that. So what we need to do is we need to figure out, is the denominator going to be positive or negative? Let's check. So I do the number line again, this time at 0. We are approaching from the left. From the left we have, on the left we have -1, -2. So let's see. I know that in my numerator we're going to get 3 as x approaches 0. And I know that in the denominator it's going to be 0. But we want to know that 5 times 0, in reality, what is it going to be, positive or negative as we approach 0 from the left? We know we have a -1 there. So now let's see. If I approach 0 from the left, it's always negative. And 5 times a very small negative number is still negative, so therefore that's negative. But notice that we have 3 over a negative number times -1. That makes it a positive, very small number. And therefore, the limit is approaching positive infinity. Let's look at this one. Limit as x approaches 1 from the right of natural log of x minus 1. So natural log of x minus 1 is one of the graphs that you need to know. Actually, natural log of x by itself. But the -1 tells me that the graph has been moved 1 unit to the right. So imagine just graphing it. So if I would graph it, just a quick graph. It's moved to the right, so the original graph, natural log of x, this y-axis is called an asymptote. So if you translate horizontally a function that has an asymptote, the asymptote also moves. So therefore, it's moved 1 unit to the right. And the whole graph itself was moved 1 unit to the right. The original natural log of x crosses at 1, 0. So that means that now it's going to cross at 2, 0. And it'll look something like this. And this one, just by looking at the graph, as we approach 1 from the right, my graph is going towards negative infinity. It is decreasing without bound. As we get closer and closer to 1 from the right, it is decreasing. So therefore, this limit will be negative infinity. Know your graphs. So now we're going to look at limits at infinity. But before we do some problems, let's look at this. If you want to take the limit as x approaches infinity, negative infinity, or positive infinity, and infinity is in the denominator, notice x is approaching negative infinity. That means this x is approaching negative infinity. Just means that it's getting very, very large in the negative direction, even though that's kind of wrong. But imagine negative 10 million, negative 100 million, and so on. Well, anyway, anytime your denominator goes to one of the infinities, whether it's negative infinity or positive infinity, the limit itself is 0. Okay? If infinity is in the numerator, for example, if x is approaching negative infinity and the x is in the numerator, then obviously it's going to be a very, very large negative number, like negative 10 million divided by 2 is still negative, and it's still large. So this also matters. So since in this case it's positive and the numerator is approaching negative infinity, your limit itself will be negative infinity. And as x approaches positive infinity, and again you have infinity in the numerator, it's just a very large number divided by 2. It's still going to be very large, so therefore it'll be infinity. So anytime the numerator has infinity just by itself, it'll go to infinity, the limit. And infinity inside square roots and logarithms, well, as x approaches infinity, well, the limit approaches infinity also. Just think of a huge positive number. You take the square root of it, it's still going to be pretty large. So as it gets larger and larger, so is the square root of that number. For this one, we do not check negative infinity because, remember, you cannot have a negative number inside the radical. Same thing for natural log of x. Whatever you have in here has to be positive, has to be greater than 0. So as x approaches infinity, the limit approaches infinity also. Now, we're going to look at some problems I have that are approaching infinity. So let's read this first. If f is a polynomial, then the limits at infinity behave like its term of highest degree. So if f is a polynomial, then the limits at infinity behave like its term of highest degree. This is what I mean. So in this situation, we have a rational function, but in the denominator, it's a polynomial. So this is what you have to look for. Make sure that if the limit is approaching, or x is approaching one of the infinities, then we can do this. We can rewrite it. Limit as x approaches negative infinity of the term of highest degree. Well, in the numerator, we only have a 1. It's a constant, so we're just going to leave it alone, 1. And in the denominator, we have x squared and negative 9. X squared is a term with highest degree. So you ignore the 9. The 9 is not going to do anything to the denominator. So now we look at this. Notice that the denominator is approaching negative infinity. The denominator is approaching negative infinity. So therefore, that means that the limit is equal to 0. Comes from here. Infinity in the denominator. Let's do another one. Again, we are approaching, x is approaching infinity. So we want to rewrite it. Let's simplify it. So limit as x approaches infinity. According to what I said earlier, it behaves at the infinities, it behaves like its term of highest degree. So in the numerator, highest degree is x. Denominator, there's only an x, so x. So no, we don't plug it in. We simplify. So limit as x approaches infinity. X divided by x is 1. And the limit of a constant is that constant. It doesn't matter if it's going to infinity. It's still the constant. So the limit is 1. Okay. Another example where the limit as x approaches infinity. Again, if you want to take the limit as x approaches infinity, then we want to rewrite it, because at the infinities it behaves like its term of highest degree. So I'm going to write it like this. Now if we look at the numerator, x squared is a term of highest degree, x squared, so it'll be x squared in the numerator. In the denominator, x cubed is a term of highest degree, so it'll be x cubed. Now we simplify a little bit, so we say limit as x approaches infinity. So if I have x squared divided by x cubed, that's going to give me 1 over x. Now I can evaluate. Notice that the denominator is approaching infinity, so we have infinity in the denominator, and therefore the limit will go to 0. Now let's talk about asymptotes. First, a vertical asymptote. The line x equals c is a vertical asymptote of the graph of the function if any of the following is true. Again, if any of the following is true. So how do we know if it's a vertical asymptote? Well, this is how you know. If you approach c from the left and you get infinity, that's a vertical asymptote at c, x equals c. If you approach c from the right and you get infinity, that's a vertical asymptote at c. If you approach c from the left and you get a negative infinity, again, a vertical asymptote. If you approach c from the right and you get negative infinity, again, vertical asymptote. So anytime you take the limit from the right or from the left and you get one of the infinities, that means that it is a vertical asymptote. Here they are. So we're approaching c, the limit is infinity, so that means we have a vertical asymptote. This is the vertical asymptote right here. And you have to write it as x equals c, or whatever the c is. Notice again, here we have the limit is infinity as we approach c, so therefore x equals c is the asymptote. Again, the limit as c approaches, the limit as x approaches c from the right, you get infinity, you get a vertical asymptote at c, x equals c. Again, as you approach c, that means from both sides you get negative infinity. Notice they're both going towards negative infinity. Again, vertical asymptote, x equals c. I think you get the picture, okay? Vertical asymptotes, vertical asymptotes. Let's go back so you can see them again. We saw them at the beginning, all of these. Now we can go back and look. When we did the limits, we got infinity and negative infinity, vertical asymptote, x equals pi over 2. Again, limit, we got infinity, negative infinity, vertical asymptote. Again, negative infinity, positive infinity, vertical asymptote at x equals 0. So these right here, that will be the vertical asymptotes. This one, natural log, as we approach 0 from the right, we got negative infinity. That means the y-axis is a vertical asymptote. Okay, now for a horizontal asymptote, the line y equals L is a horizontal asymptote to the graph of the function f if the limit as x approaches negative infinity of f of x is equal to L, or the limit as x approaches infinity of f of x is equal to L, meaning that when you take the limit at an infinity and you get a number, a constant, then that means that is a horizontal asymptote, and you write it as y equals L. Y equals whatever number you got. Here's a look. So as we take the limit as x approaches negative infinity, we get a number. So let's see, as we approach negative infinity, the graph is approaching a certain y value. So therefore, that's a horizontal asymptote, y equals L. Same thing, if we take the limit as x approaches positive infinity of f of x and you get a number, that's a horizontal asymptote. So again, as we approach infinity, the graph is approaching a certain y value, that will be a horizontal asymptote. So again, if you're taking the limit at the infinities and you get a number, then that means that is a horizontal asymptote. Okay, so now we're going to find, for each rational function R, find the domain of R, find any horizontal asymptotes of R, and then find any vertical asymptotes of R. So first things first, domain. So the domain of this rational function 2 minus 1 over x squared. Domain, since we have a fraction, we want to find the number that makes the denominator 0. And in this situation, since it's just x squared, then we know that x cannot equal 0. So for the domain, we can write just x cannot equal 0. So that means all real numbers, x cannot equal 0. For part B, we need to find horizontal asymptotes. So that means take the limit at the infinities. So limit as x approaches negative infinity of 2 minus 1 over x squared. So the limit of a constant is the constant itself. So the limit of the constant is the constant. So that's just 2 minus, here for this one, the denominator is approaching infinity. So remember what we said, if the denominator is approaching infinity, then the actual limit is approaching 0. So the limit of this function is just 2. That means we have a horizontal asymptote. Horizontal, because it's a constant, horizontal asymptote at y equals 2. So then we do the other one. So limit as x approaches infinity of 2 minus 1 over x squared. So again, the limit of a constant is the constant itself, so that'll be 2 minus, and for this one the denominator again is going towards infinity, so that means that the limit is heading towards 0. So 2 minus 0 is 2, horizontal asymptote again. Now if it's the same number, you don't have to write it twice, you only write it once. Okay, now for part C, vertical asymptotes. Usually vertical asymptotes, what I didn't mention before, is that they also occur when the denominator is equal to 0. So in this situation, let me write it out. Vertical asymptotes occur when the denominator equals 0. And earlier when we did the domain, we noticed that the denominator is equal to 0 when x is 0. That tells me that that's going to be a vertical asymptote. So this one is easy. Vertical asymptote at x equals 0. So for vertical, it's x, and for horizontal, it is y. Okay, here we go, last one. For this one, what I want to do is I want to expand it because we're going to be taking the limit at the infinities. So let me expand. So this will be x times x squared minus 2x plus 1 over x plus 3 cubed. That will give me x cubed plus 3 x squared times 3 plus 3 x times 3 squared plus 3 cubed, which is 27. Let's simplify. So if I distribute in the numerator, we get x cubed minus 2x squared plus x. The denominator will be x cubed. This will give me 9x squared. This one will give me plus 27x plus 27. So there, we expanded it. Now to find the limit, or to find, well, first we got to find the domain. So the domain, I won't look at the expanded one, I will look at this one. So for that one, I want to know when is the denominator equal to 0. That would be when x is negative 3. So domain x cannot equal negative 3, because that'll make the denominator equal to 0, and we don't want that. For part B, we're going to look for horizontal asymptotes. So we take the limit as x approaches negative infinity. Now at the infinities, it behaves like its term of highest degree. The highest degree in the numerator is x cubed, highest degree in the denominator is x cubed, so it's really behaving like if it's x cubed over x cubed, which that simplifies to limit as x approaches negative infinity of 1, and the limit of a constant is just the constant, so 1. So there we go. We have a horizontal asymptote at y equals 1. If we do positive infinity, we do the same thing. Limit as x approaches infinity. Well, it's going to be the same thing, x cubed over x cubed. So it'll be limit as x approaches infinity of 1, which is 1. So horizontal asymptote at y equals 1. Same one. You don't have to write it twice, just once. Now, horizontal asymptotes, functions can have 0 horizontal asymptotes, 1 horizontal asymptote, or 2 horizontal asymptotes, no more than 2. Vertical asymptotes, there could be many. So now, for C, vertical asymptote happens when the denominator is equal to 0. In this situation, the denominator will be 0 when x equals negative 3. So vertical asymptote at x equal negative 3. And that's it. We're done.